So we're on page 2 of your notes and we're looking at the structure of amines. Now you can think of an amine as simply ammonia where one of the hydrogens has been replaced by an R group. So if you think about ammonia, NH3, it would have 3 hydrogens around it like that. So the primary amines, these ones, we've just taken off one of those hydrogens and we replaced it with an R group. That's an alkyl group or aryl group. Basically it's carbon chain. And a primary amine, a bit like a primary alcohol, has 1 R group, secondary 2 and a tertiary 3. So when we name them, again, it's very simple. We've got the carbon chain, in this case meth, and then our amine to tell me it's an amine. So this one would be C with the 2 hydrogens on the nitrogen and 1 carbon because it's a methyl. So this would be methyl amine. So that's methyl amine, ethyl, propyl, dimethyl. You've got 2 CH3 groups. There are some ones that you need to learn. So for example, this one, phenylamine. This is what we call a benzene ring. And sometimes if it's a substitute, it's called a phenyl ring. So this is called phenylamine. If you're a biologist, you might have come across these as amino groups. So if you see here, we can call it 1-aminopropane. And if you notice, 1-aminopropane is identical to propylamine. Okay, either of those 2 names are acceptable. As a chemist, we generally use this one. We use propylamine, but you may come across it in some textbooks as 1-aminopropane. And again, 2-aminopropane, where the amine group is on the 2nd carbon, because that is a secondary amine. So short-chained amines are soluble in water, and the reason they're soluble in water is exactly the same as why ammonia is soluble in water. They can do hydrogen bonding. So if I take, for example, methylamine, I have my nitrogen, I have 2 hydrogens, and I have that CH3 group. Well, I've still got the lone pair on the nitrogen. I've still got a hydrogen, delta positive, attached to that very electronegative nitrogen, so I can still do hydrogen bonding. So you can see here I have my amine, and I've got a hydrogen bond between the delta positive hydrogen of one molecule to the lone pair on the nitrogen of another molecule. And just like ammonia, not only can they hydrogen bond to themselves, but they can also hydrogen bond with water. So this is why short-chained primary amines are all soluble in water, because this time, instead of forming a hydrogen bond to themselves, they can form a hydrogen bond to the water. They can also react slightly with water in the same way that ammonia does. In the next bit of the video, we're going to be looking at the reactions of the amines. Now, the reactions of the amines are very straightforward. You need to ask yourselves, however, what would ammonia do? Because, if you remember, all an amine is, it's an ammonia molecule that has had one of those hydrogens replaced by an R group. So a lot of the chemistry is very, very similar, if not identical. So one of the ways you can work out the reactions of the amines is you can say, well, what would ammonia do in this situation? And if ammonia does it, then the amine would do it as well. Okay, so this is a series of experiments looking at the reactions of butylamine. So we're using butylamine as our amine, and we're going to compare them with the reactions with ammonia. So the reactions of butylamines, the reaction for all amines, is very, very straightforward. You just have to ask yourself, what would ammonia do? Because the reactions of butylamine and all other amines are identical to the reactions with ammonia. Now, one of the key characteristics of all amines is they have a very distinctive smell. very distinctive. They smell of rotten fish, decaying bodies, and putrefying flesh. In other words, they stink. Please don't sniff them. Okay, so these are the reactions of the amines. And the first one I'm going to start with is looking at their solubility in water. So I'm going to compare butylamine and I'm going to compare it with ammonia. So I'm going to take a few drops of butylamine in my test tube. You can see that. And I'm going to have a few drops of my ammonia. I'll put the lid back on that, and I'll explain why I'm putting the lid back on that in a minute. And I'm going to add some distilled water. And you should see that that is reasonably soluble, as you'd expect. As you would expect the ammonia. So you can see there they're both soluble in water. If I take both of these and I add a couple of drops of indicator, you will see that this one, the ammonia, okay, makes the purple solution because it's alkali. And as you would expect, if I take the butylamine, it also makes the same purple solution because they're both alkalis. Okay, so the second reaction we're looking at is the formation of salts. So I'm going to take some hydrochloric acid and I'm going to add that. I want about 2 centimetres cubed of that. And to this I'm going to add some butylamine. So again, I just want a few drops of my butylamine. 3 drops there. Okay, now you should see that that is very soluble. In fact, it's more soluble in the acid than it was in just water. And the reason for that is that the butylamine actually reacts with the hydrochloric acid rather than just dissolving in the water. So there's a reaction going on there, which makes it quite soluble. And we're going to repeat the same experiment with the ammonia. Again, if I take my hydrochloric acid, and again I want about 2 centimetres cubed of this, like that, and I add a little bit of ammonia, and again you should see that it's quite soluble. Okay, experiment 3 is looking at the reactions with the transition metal ions. So I've got some copper sulfate here, and I'm going to add about, again, 2 centimetres cubed of copper sulfate. So that will do. And then to that I'm going to add a couple of drops of ammonia this time. And you can see there we've got a precipitate being formed. Okay, a bit more ammonia. You should see we've got a blue precipitate being formed there. Okay, so that's initially. And you won't be surprised to see that when we do the same reaction with butylamine, more copper, we get the same reaction. So here we go with the butylamine. We get precipitate. Slightly different colour, but it's this actually, that's just because of the way it's structured and how much water I've got in there and all sorts of other things. But basically I get another precipitate. Okay, so again, a blue precipitate being formed. Okay, so there you can see the precipitate that I've made between the copper and the ammonia. Now, if I add excess ammonia to this, I get a different reaction or a secondary reaction taking place. So hopefully you can see this. And you can see there it's gone from the pale blue precipitate to a dark blue solution. Now you would get the same reaction if you did that with butylamine. The reason I'm not going to do the same reaction with butylamine is that would be quite a lot of butylamine in there, and I tend to try to use only small quantities of butylamine. The reason for this is there is also one other distinctive property that all amines have, and that's they smell. Okay, so the last experiment we're going to be doing, as you can see, we've moved to the fume cupboard because we're going to do the reaction between the amine and ethanol chloride. So ethanol chloride is quite a reactive reagent, so that's why we're in the fume cupboard. So I'm going to take a little bit of my butylamine. And to that I'm going to add my ethanol chloride. And I need another dropping peck. Can you just grab me one, Charlotte? Yeah, right, that's really going to work, isn't it? It's fun. Let's go. So I'm going to take my ethanol chloride and I'm going to add just a few drops of this to my butylamine. I'm going to do that very carefully. And I'm going to turn the fume cupboard on because it's quite a vigorous reaction, so I want the fumes to be going in the right direction. So you can see there you've got copious amounts of steamy fumes, also producing some white smoke. It's a very vigorous reaction. Reactions of the amine. So we've looked at the practical now, and now we're going to kind of talk through the theory behind it. So the reactions we were looking at was of ammonia and butylamine. So ammonia has the formula NH3, and butylamine, basically we've just replaced one of the hydrogens with the 4 carbons to make the bute group. We've still got our nitrogen with our 2 hydrogens on it. Okay, so if you remember back to the practical itself, when we added a few drops of the full range indicator, it went purple, showing that the solutions are basic. Generally speaking, they are sparingly soluble or soluble in water, depending on the length of this R group here. So the longer and longer this R group becomes, the less and less soluble they are. So it very much depends on the length of this R group, whether they're soluble or sparingly soluble. So I'm going to write down sparingly soluble. Okay, so the molecular interactions that allow them to dissolve is the fact that they can form hydrogen bonds. But there's something else which again will help them to react, and that is the fact that they can also react with water. As well as forming hydrogen bonds with the water, they can also react with it. So butylamine, I'm just going to use R to stand for most of my carbon chains. So I've got my amine functional group there, which is what I'm interested in, and it can actually react with the water, and we'll cover this more in a later video, to make, I should just say that's very reversible, to make N with an extra H on it, and this becomes positive, and you get OH negative. As we saw, the salts were much more soluble in an acid than they were in water, so they were more soluble. And that's because water is a very weak acid, but hydrochloric acid is a much stronger reaction, much stronger acid. So they're doing a very similar reaction, but just the acid makes it a much more feasible reaction. So again, if I take my fish on the bottom, and this time I'm adding hydrochloric acid, same reaction is going on. This is accepting that hydrogen ion. This is an acid-base reaction, positive, and Cl negative. So that's the reaction taking place there. So the third reaction we saw was between our amine and our ammonia and our copper sulfate solution. So we saw the same reactions. So firstly, we saw a blue precipitates with a small amounts of our ammonia or our amine, and this works both for ammonia and for amines. And we got a dark blue, blue solution with excess. Okay, now this is a reaction again we're going to study in a lot more detail in the transition metals pack, but it's actually a two-step reaction. The first step is what we call deprotonation. So that basically does exactly what you think it does. It removes a proton, deprotonation. In the second step, we have a reaction which is called ligand exchange, where we're removing some of these water and some of these OH negative ions, and we're replacing them with ammonia ligands. And this is my blue precipitate, and this is my dark blue solution. Now the reactions for the amines are identical. Basically, all you're doing is you're replacing one of these hydrogens with an R group. So this becomes 2NH3 positive with the R group. So it's 2RNH3. And here you're replacing one of these hydrogens again with an R group. So the reactions are identical. So have a go at doing those. Okay, so there you can see that we've got the same reactions. So all I've done is I've replaced one of the hydrogens with an R group, but they balance in the same way. This produces the same precipitate. It's just wherever I had an ammonium ion, I now get the NH3 positive with the R group attached. Wherever I've had an ammonia, I get an amine group attached. But it's basically the identical reaction. Okay, and last but not least, we have the reaction of the amine with that acyl or acid chloride functional group. So you saw me doing that in the fume cupboard, and it's a very vigorous reaction. And you should have seen steamy fumes followed very closely by white smoke and lots of it. Okay, so the electrophilic area that is attacked, double bond O, because you've got a delta positive there, and you're breaking the bond between the carbon and the chlorine in the acid chloride. So if we look at the reaction, so you've got your acid chloride, CH3 bonded to C, double bond O, Cl, and we're going to add our amine group to that. So again, I'm just letting the R group stand for the carbon chain. So this group here is going to come off with one of the hydrogens. So that's the HCl, the steamy fumes. And you're going to get left with the CH3C double bond O. This R group is still there. So you've got your nitrogen and your R group, one of your hydrogens is left. Now, you would have seen the steamy fumes. The white smoke comes from the fact that this HCl will react very rapidly with this group here, with this amine, and that's why you get that copious amounts of white smoke that you saw. So you get an N substituted amide. So this is my product. This is what we call an N-substituted amide. It's called an N-substituted because there is an R group here substituted directly onto the nitrogen. And this would be called N. If I started with butyl amine here, this would be N-butyl ethan, because I've got 2 carbons here, and amide. So we stick the amide on the end. So it's N-butyl, so this would be my 4-carbon chain here. Eth, because I've got 2 carbons here. Ethan, and then it's an amide because I've got this R group here. And we're going to be studying the amides in a separate video.